All right, mic check, I'm good. So I'm Max Ceron, CWB Association Welding podcast. Today we have a really cool guest, Welding podcast.
The show is about to begin.
Hello and welcome to another edition of the CWB Association podcast. My name is Max Ceron, and as always, I'm out there looking for the best guests I can find for everybody out that watches the show and listens along. Today, we have someone who is tied to or was tied to one of our affiliates now and now has branched out on his own. We got Mark Norfolk, and he's coming to us here, and he's the owner, president, and all things incoming of Fabrosonic. Mark, how you doing today?
Very well. Thanks for having me. Good morning.
Good morning. So, where are you? What's your location?
So we're just north of Columbus, Ohio, so kind of Midwest.
So, are you still warm? Is it cold? Is it raining? What's the season like right now?
Yeah, so it's we had a little bit of snow this weekend. I'd call it flurries, nothing much. So, but it's supposed to be warmish, 40s today. So it's not too bad. A little dreary, but other than that.
That's all right. I know. I was watching the Browns game on the weekend. I'm a big Browns fan, and
I'm
saw
sorry.
No, we're having a great year. We're 7-3. I'm happy. But I did see that the field looked a little frozen, and I was like, oh yeah, it's getting cold down
Chilly.
there in Ohio. Yeah, which is good because I got about 6 inches of snow here in Canada already. But so I can pretend it's nicer when I watch TV.
Somewhere else. Yeah, I love it.
So are you a local? Were you born and raised in Ohio? Like how did you end up in outside of Columbus?
Yeah, I'm born and raised in Columbus. My career has taken me other places, but always ended to make it back. My wife's from Cleveland, so she's a big Browns fan, which is why I offer my condolences. I've seen her suffer over the last 25 years.
And then in terms of where you kind of had your career, right?
Yeah.
Did you always work in the Columbus area?
No, so I'm an Ohio State University welding engineer by training.
Okay.
That's my welding background. After school, I spent 10 years with John Deere, making tractors and other things. So I was in Iowa, Mexico, Illinois, a little bit of everywhere, bouncing around. But after about 10 years of that, my wife said, hey, I'm moving back to Ohio. You can come or not, but I'm moving back to Ohio. So here we are.
That's an interesting connection with John Deere because I worked for Brandt Industries here in Canada for almost 10 years.
Sure.
And they own most of John Deere up here in Canada. They just
Yeah.
Well, over the last decade, they've been slowly buying up pieces of it all over the place. And I worked with the attachment department where we would figure out how to make all the different attachments fit on basically every other type of vehicle it's not supposed to fit on. So
Yeah, I love it.
that was
My
a lot of fun.
my first 3 years at Deere were all in tests, so I got to drive all over the world, testing different pieces of equipment, doing all sorts of things that you shouldn't be doing. I think I might have a world record. I got a fully loaded combine. I got air on all 4 tires when we were trying to do some experiments. So that may be a world record. I don't know.
It's funny because I used to bug a lot of my farmer friends. I live in an agricultural center here in Canada, and I live in
Yeah.
Regina, Saskatchewan. So we have the headquarters for Brandt here, and they hire probably 2,000
Everybody.
welders. It's a big shop.
Yeah.
But I used to always bug them. It's like, oh, you're working on a combine. Yeah. And what does it combine exactly? And they would look at me and think like, well, it's just called a combine. I'm like, well, why would you call it a verb? I'm sure there's a reason. And then they think about it and be like, well, I guess it combines a bunch of other processes that used to
Into
get
one
them
machine.
into one machine. And I used to love just hammering the new guys on that because a lot of people just
What?
think about what a machine is called. They don't think about why, right?
Yeah.
Like,
I
So-
love it.
so what is your background in education then? You're a welding engineer. No one generally signs up for college to be a welding engineer.
Yeah.
Usually it's a path you kind of fall into or find somehow. So,
Exactly.
how did you always want to be an engineer in general? Did you have kind of a welding knowledge maybe before college at all?
I knew zero about welding coming into this. So I always wanted to be an engineer, didn't know what type. So I kind of signed up for electrical engineering. and took my first electrical engineering class and decided, well, maybe Fourier transforms are not a passion in life. And they had an engineering day where all the different disciplines came out, and there was a booth for welding. I'm like, I got to check that out. Took a class in the welding program, and then I was hooked. Yeah,
That was it.
just got into it, loved everything about it. And like I said, 10 years at John Deere. While I was in college, actually, I was designing arc welding cells for John Deere. So John Deere kind of paid for the last 2 years of my college by just giving me a computer and doing weld cell, development remotely. So lots of fun times.
That's fun. That's fun. I used to have to do weld cell development, and it's as long as you got someone that's willing to pay for the bill for your ideas, it's a lot of fun.
It can be.
Now, you're lucky that you were at a college that offered weld engineering, because that's not something that's offered in very many places.
Now it's a really small program, and there's only 2 or 3 in North America, so it's it's a small group.
So once you fell into the weld engineering spectrum, it's not like you narrowed yourself down at all. It's almost like you just picked the scab off of a whole giant new injury. So
exactly.
what did you start thinking about as you started looking at this welding engineer life ahead of you, where you could either go into research or design or metallurgy or materials or all these crazy things you could do? Where did you kind of see your place in there?
So I didn't have like a great plan. I kind of stumbled through it. The thing about the welding engineering programs is they typically are fairly broad. So, you're, really, really shallow in lots of topics. So you can kind of pick and choose what topics, are fun to play in. Certainly robotics was a lot of fun for me. And, that led to a lot of gas metal arc welding kind of development. And then from there, doing the robotic weld cell design. From there, developing new procedures for manual welders. And then from there into a whole world of tests, because of course, where do all the machines fail at the weld? So, kind of fell into all these different paths, as I went along with no great plan. But again, you kind of get that wide berth of information that then lets you fit in kind of anywhere. And actually, John Deere for many years was the number one employer of new college grads out of the welding engineering program. Because you have that broad base of manufacturing knowledge, they can kind of take a welding engineer and put them in anywhere in the manufacturing space. And, they know a little bit of metallurgy, a little bit of double E, a little bit of mechanical engineering, have a lot of hands-on experience, can talk to someone on the shop floor. So the welding guys always did really well at Deere.
It's I love this connection. It's like the 6 degrees of Max, because it was like we used to always poach engineers from John Deere at Brant before we started buying pieces of John Deere, because of the exact same things you're just saying. I remember we brought up an engineer from Mexico, the John Deere Mexico plant, and he was wonderful. Like, he knew a little bit about every single process we had. He had that great, like, well-rounded use, but that even in itself is a very niche type of industry, because not too many companies allow engineers to have that freedom of exposure, and that's something I think that actually makes a lot of engineers hate their jobs, that they end up being in a company where they're just they're in a tight little branch of whatever company they're in, and that's what they do morning to night every day, and they don't really get to be a part of the bigger picture or the bigger design, whatever that is, and it's kind of like a nail in a coffin to a lot of people that enter the engineering world.
Deere was a great company in that they did move people around a lot, get people into different experiences, getting crosstalk. My favorite day of the year every year is Deere always brought in the engineering team to the factory floor at least once a year and actually had them assemble stuff, weld stuff, assemble stuff, build stuff on the line. And the number one day for design changes was always the day after that, because the engineer's like, oh, what idiot did this? Oh, yeah, it was me. I can go fix that. So you always got that development, that interaction, that, trying to make people broader in how they think. So it was always a good company for that.
I get quite a bit of flack on the show for always interviewing so many engineers. I got told I went to the dark side as a former welder,
Yeah.
and it's like I got it's such an interesting, uh, you know, relationship from the fabricator welder to the engineer. They both obviously need each other. Like it's
Yeah.
a very clear connection that this is a marriage that needs to occur.
Used to happen.
It needs to happen, but when the welder says something's not fitting, it's like, telling your spouse to calm down. It's not going to get you very far, right? So I remember being on the floor and trying to
Yeah.
be like, look, man, this is not going to work. And they're like, no, no, no. The computer, it's like the drawing's good, man. It's like, but in reality,
Tolerance stack up.
yeah, it's not actually gonna work. It's like,
Yeah.
and it was a really great experience. But for yourself, 10 years, almost 10
Yeah.
years at John Deere, then
Yeah.
where did you go from there? Like,
So
that
from there,
sounded like it was right out of college.
yeah, right out of college, 10 years with
Yeah.
Deere, and then back to Ohio. Started working for a CWB affiliate, EWI. And in that position, totally different world. I ended up managing large government research programs. So
Oh,
EWI does research and development in new manufacturing technologies, new welding techniques. And so I was a program manager for a bunch of government projects developing new welding techniques for mostly defense related items. So got to spend time at Electric Boat, working on nuclear subs, got to do work with the Department of Energy down in Oak Ridge, got to do work with the Department of Energy out in Colorado on wind turbines. So kind of just this broad base of all kinds of weird stuff, heavy knowledge in manufacturing and welding, certainly helped me out, but I got exposed to all kinds of new products and toys that I never had seen before. So, that was an interesting, probably 7 years. Yeah.
so would you feel, in comparison to the Deere work,
Yeah.
that you got exposed to more on the design side, but perhaps less in the practical application side?
Yeah, I think at Deere, the welding engineers got involved with stuff, but most days we were welding 1018 steel, and every once in a while they'd throw in a 1020 just to really get excited.
Fancy
And
it up.
once a year you'd have something that touched wet crop, and you'd get to play with 304. So I mean, moving to EWI, and then I'm starting to look at Inconels, Hastelloys, 150 KSI steels, things that,
Mhm.
with a metallurgy background, it's like, oh, this is all stuff I learned about in school, but never got to play with. So
Yeah.
all of a sudden I'm working in all kinds of different new material systems. So yeah, less on the design side, but a lot more on the, real deep metallurgy that I never really played with up to that point.
And in terms of like the follow through, this is what people always ask about research companies,
Yeah.
universities and stuff like that. They
Yeah.
get big projects, they get big research projects. You know, Working at EWI, do you get to see them through? Like, here's the project right from the start, the first call. We want to do this crazy thing. You're
Yeah.
like, yay! I'll help you figure out this crazy thing,
Yeah.
and then it goes out the door. And what happens to it then?
Yeah, so it's a mixed bag, just like I guess everything else in business. So, I worked on a project for Electric Boat, designing a new process for putting some stuff together. I'm not going to go into details, but that's in production today. I know the engineers there, and they're still up and running today. So, the team put together this package, and it's making equipment today for our sailors. Another example, I was doing work. This was more on a commercial basis. We were doing work with a company that makes fire doors, and we were doing MIG brazing of steel panels together at ridiculous speeds. It was multiple heads, twin arc. I don't know, like 300-400 inches a minute travel speeds. I mean, we're cranking these doors out.
It's hustling.
Yeah, and we got this the system figured out, got everything running, and like 6 months later, the company went bankrupt. So it's like, I mean, this is a home run from a technical standpoint, but the rest of their business just didn't mesh. So, it's a mixed bag. You see it, from all aspects. You definitely get the technical wins most of the time,
Yeah.
but the business wins, aren't always under your control. But
Yeah.
we do get to see what happens, just not always the result we're hoping for.
I wonder what happens to that IP, that goes to that company that goes bankrupt. Do they sell it off or do they die with it? You wonder, eh?
Yeah. You always wonder what else could we have copied and pasted that on and made a real big difference because it was
Things
flying.
things don't tend to die, right? Like
Yeah.
sometimes they'll fall under the radar for a while, but then you see them rebirthed somewhere else in a different format, and you're
Yeah.
like, oh, there's that tech that I saw 5 years ago that I thought disappeared.
Yeah.
People don't usually let advancements just float away,
Sit. I
So
think in
go ahead.
2007 I was working on spin arc where you take the nozzle and you kind of spin it a little bit to get your metal to flow up for a narrow groove weld. You get the metal to flow up and get a little bit better penetration. I was working on that until like 2007, and I think it's changed names by 3 different companies since then. So that technology's been around since like 2000, and every 4 or 5 years someone comes out with a new version of it, trying to get deep roots.
I've always actually thought that was a pretty interesting concept because
Yeah.
very automatically you would think of lots of benefits.
Yeah.
Even the vibrations, the frequency of the vibration would help
Yeah.
with, I would think, the settling of the grain. Like
Yeah.
it would you would think so, and the heat should be exactly the same, really, because contact doesn't get
It's just
lost,
moving the fluid around.
right? So it's
Yeah.
basically just using that kinetic energy or that centrifugal energy to push it out, right? So
Yeah. For narrow grooves, it produced amazing results. I mean,
yeah.
1 degree included angles, and you get, great tie-in.
Now, what about cost of these things? Like
Yeah.
it comes up because EWI, from my, I'm fairly new to EWI, and this was actually interesting to me and something that I deal with now at CWB in terms of where I work and what I do with the membership, is
Yeah.
that I worked as a welder for 27 years. I worked with some of the biggest companies in Canada, and we never really had to reach out for R&D. Like it
Yeah.
was like it seems like a very specific type of industry that reaches out to a third party that says, look, we're going to drop a couple $1 million or whatever to
Yeah.
try to figure out something that's a problem in our company. I would say most companies tackle that themselves internally with staff or hiring or whatever they need to do. So for a company like EWI that deals with these large, you know projects or ideas,
Mhm.
how does that help the small to medium business welder?
Sure.
Is there a connection there? Is that just not on the table? Or can Bobby Joe's welding down the street benefit from an R&D giant like that?
Yeah. Well, so that model I think's evolved a little bit over time. You go
Hmm.
back to the 90s and the 2000s, and EWIs, they were cranking out research for large oil and gas companies who could fund these major programs. But I think as the labor market is really constricted, the R&D components at many companies, even mid-sized companies, has kind of disappeared. And having that ability to bring on 200 experts in a field to solve a specific question, it doesn't have to be a huge program, but get you the resources. It's basically outsourcing your R&D department to different experts. So I've seen that kind of shift from the huge companies to the more medium-sized companies. Now on the small end, it is kind of tough, just because of the economics.
Yeah.
You got a bunch of PhDs, often in the lab doing work, so that's going to cost something. And where most of the benefits we've seen are in kind of government private partnerships. So there's a program in the state of Ohio. There's a program in the state of New York where companies that do these types of manufacturing R&Ds are funded partially by the state to do work with especially small businesses.
Yeah.
So a lot of that's coming through some federal programs, but overall, just like in racing, the technology on your F1 car, eventually, those turbos make their way down to the
Hmm.
Toyota Supra, right? So
Yeah.
all these things that do get invented as they're used more and more and become more prevalent, then that kind of, works its way out slowly, but it is a long process.
Yeah. It is something that, I've talked about on other shows. It's like I call it the hobby effect,
Yeah.
that technology doesn't become a real thing in society until you can do it for a hobby.
Yeah.
So like, I mean, robots, I remember 25 years ago, the first robot I saw was like $10 million and it ran for like an hour a day because it was constantly not working. It was like a constant battle to get this thing to do one weld. And it'd be like, yay, it's dialed in. Let's do two. You know, and to now where you get $40,000 cobots,
Yeah.
and you could now realistically, I think I see it within the next couple of years, be able to pick up an $8,000 to $10,000 cobot for your garage to play with. And I think at that level, once you get to that point, technology is embedded in society. Now it's a thing. It's like the 3D printer. It was like this ridiculous thing, but now I can go to Home Depot and buy one for $200.
Buy one. Yeah.
Right. So like, I mean, now this technology is real. And like the example with, Formula One racing, and now, my lawn, you can buy turbo lawn, one cylinder lawnmowers for crying out
Right.
loud.
Yeah.
Like
it eventually trickles down.
yeah, it does eventually trickle down, but it is a long process. Thank God technology trickles down better than money, because we
Right.
know that doesn't work.
That doesn't work at all.
But if it could be streamlined, like you said, through granting and products, and I mean, I think even the connections that we're seeing now with companies around the world post COVID, where collaboration's kind of back on the table.
Right.
Pre-COVID, I felt like everyone wanted to be the monolith. Right? Everyone wanted to develop the next Amazon or the next eBay, or everyone wanted to have these monolithic, centered companies where they just ruled everything. And COVID kind of just leveled that all out and said, no, it's not going to work.
We need to work together.
We need to work together, and we're seeing a lot of affiliations and partnerships and collaborations with companies around the world because it makes sense. Like, hey, I'm a welding manufacturing shop and I need, these parts machined. I'm not going to build a machine shop now. I'll just find a machine shop down the street to work with, and that's everyone wins, right? So
then you build those relationships, and if you need something, right away, hey Joe, can you fit me in today?
Yeah, that's exactly it. So where I'm leading with all this is, you left EWI. So it sounded like you had a really good gig there. What pulled you away from EWI, and then where did you go?
Yeah, so one of the programs, I was managing large government programs. One program that I was working on was developing a new solid state room temperature type welding process for thin metal foils. It was actually being developed for some government programs in the armor space, and got involved with that technology. We went after a few grants to prove that technology out at a fairly large scale, and got those grants. And I kind of was managing those grants from contracts, PM
Manager,
project management, and started, on the weekends dabbling with the technology, playing with the machines, running the machines. And the next thing you know, I'm running the machines, 3 or 4 days a week. I just kind of, got sucked into it. So at some point, it was about 2011, EWI actually spun that technology out as a for-profit subsidiary. So we spun out this company called Fabrosonic to do metal 3D printing at basically room temperature. And so in 2011, the way I phrase it is I made enough people angry at EWI that they said, here, go take this and get out of our hair. And so now I'm off doing this, full time.
So Fabrosonic was an EWI developed technology, right? Yeah. That then got spun out into an independent for-profit, still under the umbrella of EWI.
Still majority owned by EWI, but there are some other investors. Yeah,
I see. Okay, and then your place was you are also one of those shareholders.
Kind of, sort of, not really. More president and CEO.
Okay, I see.
Yeah.
And then did it move off grounds? Did it move into a new building? Is it this like now its own baby growing on its own?
Yeah, we have our own building, our own staff, our own facilities, all off on our own. Certainly, we still talk with EWI, but we're about 25 minutes north in our own facility. Everyone here is a Fabrosonic employee.
Okay. So what is Fabrosonic?
Yeah, so people are generally familiar with 3D printing. So in metal 3D printing, we're typically going to take some sort of powder or maybe a wire, and we melt that in specific locations to build up additively material. So we're taking a CAD file, slicing that into layers, and then using some sort of fusion source to build up layer by layer. Fabrosonic kind of turns that on its head. Kind of the first thing is our welding technique is ultrasonic welding. Ultrasonic metal welding is not a new idea. It's been around since the 1960s, mainly used in electronics for wire bonding, they call it. It's very much akin to a friction weld or maybe an explosion weld. So we're taking this solid state, no melting, low temperature process, and we're using that to print thin layers of foil. So this is kind of, the idea. We're taking thin layers of foil and then welding those together into a solid material.
Okay.
The nice thing about welding with this particular setup is max temperatures in our welders maybe 100 C, and we hit that for about 100 milliseconds. So from a metallurgy standpoint, the material coming in and the material going out are exactly the same. We haven't changed the grain structure. We haven't changed precipitate size. We haven't changed anything. Another kind of benefit is metal foils are a commodity. So, if you look at 3D printing materials, even some of the wires, and definitely the powders are quite expensive. Metal foils you can buy to an existing spec on the open market. So like our number one material is aluminum 6061. And right now we're paying like $6 a pound for that material.
That's like one of the most common metals on the planet.
Right. And you can buy it from anywhere.
Yeah.
So how do we make a three-dimensional shape? That's kind of the key piece. So our incoming feedstock, if you will, is this metal foil. So we use a welder. It's a rolling device. It's about 27 millimeters wide. It rolls over the material, and anywhere that it rolls over becomes 100% dense metal. But we're basically making blocks. So if we want to make a pyramid, we make one block, then a smaller block, then a smaller block, and a smaller block. But how do we get the exact shape that we're looking for? So what we did is we actually combined our metal 3D printer with a CNC mill. So in the additive space, this is called hybrid additive. So we have CNC milling plus additive in the same box. So all of our internal and all of our external shapes, our geometries, all derived from the CNC mill. So all of our internal passageways, if we create internal structure, those all have CNC quality surface finish and accuracy. Same on the outside. Everything has the same CNC quality surface finish and accuracy. So combining those two, we'll weld for a while, weld layer by layer by layer, come in with the CNC mill, all in the same device, all at the same time in one datum. We're not moving parts around from machine to machine, and mill those geometries into the part as we go. And it's kind of a unique way of doing 3D printing.
I love this. So right now we're going to take our break. I've already written down like 6 questions on that spiel because it's very interesting to me. And I, in my mind, I see some immediate risks, which I want to ask about. So we're going to take a quick break here on the CWB Association podcast with Mark Norfolk, and we'll be right back after these messages from our sponsors. So make sure you guys stay tuned.
The CWB Association is new and improved and focused on you. We offer a free membership with lots of benefits to anyone interested in joining an association that is passionate about welding. We are committed to educating, informing, and connecting our workforce. Gain access to your free digital publication of the Weld magazine, free online training, conferences, and lots of giveaways. Reach out to your local CWB Association chapter today to connect with other welding professionals and share welding as a trade in your community. Build your career, stay informed, and support the Canadian welding industry. Join today and learn more at cwbassociation.org.
And we are back at the CWB Association podcast. My name is Max Ceron. Today we have Mark Norfolk here from Fabrosonic. So, right before the break, you're running us through. We got foils.
Yeah.
We put the foils together. It's not electricity. This is because electricity would be mayhem within that much contact surface. They would not bond equally. So you're using, it sounds like, some pressure, ultrasonic heat created through some type of directed device to that area to adhere it to at 100 C, which I don't even understand how that necessarily adheres unless it's just the vibration kind of letting them mesh at a granular level with just enough pressure so that you're not, pushing things out of shape. Am I on the right track here?
You're on the right track. So
Okay.
the key piece to understand is metals really like to stick to other metals.
Yeah.
In fact, if you look at some of the early Gemini missions in outer space, NASA was launching these aluminum capsules into outer space, and right before they launched it, everything got cleaned really, really well. So when they opened and closed the hatches in pure vacuum, they got the hatches started sticking. They actually had to kick some of the hatches open and closed because they were sticking really bad. And NASA started investigated this, and it figured out it was cold welding. So what's cold welding? So if we have two metals that are completely clean, the oxide is removed in a vacuum, and we press them together, we can get a solid state bond. Basically, the atoms, you push them close enough together and they start sharing electrons. So why doesn't that happen on Earth? If I take an aluminum plate and aluminum plate, they don't stick. The thing is, down here on Earth, every single metal surface is covered with an oxide. So kind of the key thing for any solid state joining process, friction welding, explosion welding, ultrasonic welding, is to get rid of that oxide. And how we do that with ultrasonic welding is we take the two parts and we vibrate them together. The vibration is on the order of microns, 20, 30 microns. But we go back and forth, and we do that 20,000 times a second. So we take the two metals and we scrub them back and forth. That grinds away the oxide layer. Apply a little bit of pressure, and you kind of collapse the asperities on the surface of the metal. And you have metal on pure metal. They start sharing electrons, and you get a solid state bond.
Okay,
So
now what are the dangers of oxides creeping in? Like, there must be a width maximum for bondable surface area.
Yeah. So the limitation is actually on physics. The ultrasonic welding device is acoustically tuned, kind of like a bell, to ring at a specific frequency. And about the widest we can go is 27 millimeters due to some physics reasons.
Mm-hmm.
But that being said, we're usually doing this in an open environment. So oxygen is everywhere. So as we scrub, just like you said, we include a little bit of oxide into that surface. Now, if you look at it under a regular optical microscope, you're not going to find it. But if you go into a scanning electron microscope, you see these little rocks. They look like boulders inside of our bond line. And those actually do hurt our performance. So in the X and Y kind of plane, whatever our incoming material property is, we get that in X and Y no matter what. But in the Z direction, we lose about 10 to 15%, and that's 100% attributable to those oxides getting included. So, we're always trying to improve our process to lessen the amount of oxides that get in. But, it is what it is. We do take a little bit of hit in the Z direction, and we just understand that, and we make sure our design's taking that into account.
There's always an allowable limit for everything. So, the metal on metal conversation is something that I think a lot of gearheads learn quickly when they're young with stainless steel components.
Steel. Yep.
Yeah. So, I remember being a young guy, and I bought my first stainless steel heads for a 69 Chevelle that I had. And they were like, stainless steel exhaust going onto an aluminum head. And I used stainless steel bolts. Don't ever do that for all the people that are listening, because they weld themselves in and they never come back out. They never come back out because stainless steel has much less oxides, plus it's a much harder, denser material, and it's not good with heat either, really. And it really basically welds itself in. Not even if you don't even start the motor, you can just screw that bolt in,
Let it
try to
sit.
remove it, and it's never coming out. And I remember my dad was a boilermaker and a metallurgist, and I remember I screwed that up, and he explained it to me. He's like, "Well, stainless is it just welded itself in there," and I was like, "What? How?"
Crazy.
Like, but now you have this. So with that, what I know about stainless in that situation, does stainless work well in this foil setup?
Yeah.
As kind of a, I mean, the oxides for stainless are kind of a different beast than many other metals.
Yeah.
Is that beneficial or detrimental?
So stainless steel is not really a problem. If you look at most
Mhm.
metals, your aluminums, your steels, the stainlesses, even the nickels, even kind of
Like
oddball
coppers
things
and stuff like that.
like things like molybdenum,
Okay, right.
all of those, the oxides are very brittle compared to the underlying material. So
Mhm.
when you take those and scrub them, the oxides, although they're quite a bit different material to material, they're all very brittle compared to the underlying metal.
Okay.
Some of the exceptions to that are things like titanium and zirconium. Both of those, the oxides are actually way more ductile than the underlying metal. So we have a lot of problems with the titaniums and zirconiums because the oxides are basically soft. But for a majority of the metals out there, it's very brittle. We just and it breaks right
Mhm.
off.
And what about doing it in a vacuum or in an inert gas space
Yeah.
like argon? Would
Yep.
there be benefits to that? I mean, obviously,
Yeah.
aside from the expense of trying to create that vacuum, does it help?
So we've recently done some work, for NASA welding in a vacuum. You can imagine what their uses may be, and yeah, it definitely does help. As you mentioned, the thing that keeps us from doing that is cost. We've looked at maybe putting a little laser stripe scanner right in front of where the foil goes in, and then spraying that with argon or nitrogen or whatever shielding gas you're interested in. And it does work. We can knock that oxide away, but the cost benefit just hasn't been
Right.
there for us. Welding in open air with no temperature, all your safety stuff goes away. All your, plant equipment goes away.
Mhm.
It's basically a CNC mill with nothing added to it. So it's
Yeah. At some
there's
point,
a
you start
certain amount
going
of simplicity.
backwards. Yeah.
Yeah, yeah.
Now,
Uh,
with the CNC side of it, does it do it throughout the process in intervals as needed? Like the heads just go back and forth with this? And then how do you add the layers? Does the machine come in and add more layers of a bigger piece, weld where it needs, cut it out? Like, visualize us through this.
Yeah, there's kind of two different methods that we use for presenting material. The first is a coil feeder. So we take strips about an inch wide, and we have that on a continuous reel. And so all it does, the machine is kicks out a foil. The welder comes down, welds it, and it pulls that foil along the length. And then when it stops, there's a little a little guillotine that cuts it off. And
Mhm.
we keep laying foils layer by layer, side by side, just like kind of like you're mowing your lawn. You do
Mhm.
one, then you go a little bit to the side, a little bit to the side, and then you go up. And that method is great for what I call low volume, high variability. So if the machine is going to make 100 parts and they're all different, that's great. It's very flexible. It can do all kinds of shapes, but it is a little bit slower. If we're going to do higher volumes, we'll have sheets that are kind of pre-stamped out. And we can lay them in by hand. We can use a robot. We can use a little piece of automation to lay that sheet where it needs to be, and then the welder comes and welds back and forth. In either method, that X and Y plane is going to be 100% dense. When we weld two foils side by side, we actually overlap one a little bit, say, I don't know, a thou or two.
Mhm.
And what that does is it allows that welder to, as it's vibrating, it actually runs that down, and we get a bond to those two side edges.
Along that Z axis there.
Yeah,
Yeah.
exactly. So either way, it's the same. And then either way, we use the CNC. In some of our machines, the welding device is actually another tool in the tool changer.
Mhm.
So to the CNC, it's just another, it's tool number weld, instead of tool
Mhm.
number 8. In our larger systems, usually the head is on kind of a secondary Z axis, we call W. But it just kind of depends on the machine and what we're trying to accomplish. But we do have machines that build all the way from 200 millimeters by 200 millimeters all the way up to 2 meters by 2 meters build envelope. So, really for us, is the CNC is a motion system, and we can buy any motion system size we want, and kind of put this welding device into the mix.
And what about issues with high-low within the material? Like no matter how precise a roll of consumables you're ordering of this foil, there's going to be variations in thickness or even grain structure within that. Is that affected by? Does the machine get affected by that, or does it kind of level it all out through the vibration?
Yeah, the vibrations are pretty interesting. Under a high power ultrasonic field, metal actually flows fairly easily. There's an ultrasonic effect called the Boschlinger effect, but it allows metal to flow pretty easily. So if we weld a 6 thou, let's say a copper foil, we take a 6 thou copper foil and we weld that down. Once we're done with that weld, we'll actually measure about 5.8 thou. So we are thinning the material a little bit. So, as long as the variation is only in tenths, it's no problem. We're pushing down on that with some force. And if we see, as we build up, we get to layer 200, we see that, the build's starting to get a little bit of out of flat.
Distortion, yeah.
We have a CNC mill there, deck it and keep going.
Yeah.
Same thing if we have a mistake, a bad weld, the power goes out, whatever, mill that layer off, start over again. So
yeah,
it's a great process for making mistakes, because you make it and go, oh, okay, mill it off, do it again.
Well, and it sounds like the materials you're using to build with aren't extremely expensive either. So there's not a lot of heartache with like, oh no, we just peeled off $18,000 of material or something,
Yeah. For the most part, historically, we've been in aluminums and coppers. That we have done some expensive materials. We've done a lot of tantalum recently for some radiation shielding, and that stuff you do cry a little bit when when you mess up. That one hurts a little bit.
What about dissimilar steels? Because obviously full weld, like liquid pool welding, standard welding is not very friendly to dissimilar metals. They want to migrate away from each other as much as they will. Initially bond down the road, they don't want to stay bonded. Now, do you have those issues with this type of welding, saying copper to aluminum or copper to steel or something like that?
So the beauty of solid state welding is we don't have to worry about most of the metallurgical consequences you would have if you melt it and resolidify it. So let me see. This is layers of titanium and aluminum. This is actually an armor product for a satellite, so it stops space debris. But you can see we have, good welds between those two materials. Here's another part. This is a copper face of an aluminum heat exchanger for a satellite. So this is a radiator for a satellite. And you can see we've got mixed metals there. So really, our process really doesn't care about mixing metals. Layer 1 can be aluminum, layer 2 can be titanium, layer 4 can be molybdenum. And you can kind of stack that, which is really an advantage for making some of these complex parts. Where you have the concern is if you have a part that maybe goes up to really high temperature in operation.
Right.
So when you get up to those high temperatures, metal A can diffuse into metal B and then cause you some of those metallurgical consequences. So we always have to talk to customers, how are you going to use this? What's the use environment? But if you're leaving it, terrestrial normal use, the mixed metals, we can pretty much combine anything.
Now, aside from these really advanced, purposes that I see with this, what would be some of the, around the house or, when we talk about at the beginning of the show, that trickle down, where do you see this technology trickling down into maybe our everyday uses?
So our number one use by volume is actually in electric vehicles. We have a customer that made 24 million parts last year, and they're on target for about 30 million parts this year. And if you think about an electric vehicle, there's all kinds of areas where you might want to take aluminum, copper, and nickel foils and combine those for battery type things. So high volume stuff is out there. You can drive a car today that has our technique in it. We just can't tell you whose car it is. But they're out there. You can
what does it rhyme with? No,
I'm not saying. But when you when you get to more kind of everyday uses,
Mhm.
we actually do a lot of kind of awards and signage, and I'd say almost decorative stuff, because
Okay.
we can mix metals together. Layer 1 can be gold, layer 2 can be silver, layer 4 can be copper, and then you can mill into those different layers to get very interesting.
Expose those colors, yeah.
I mean, we do a lot of work for artists and jewelers, and honestly, the jewelers' money spends just as well as the automotive, just as well as the aerospace money.
Mhm. Well, even on
Um,
your background with the little Fabrosonic piece that you were holding
yeah,
up to us, you can see the copper exposed through the
closed out.
aluminum top, right?
Yeah, so we do make kind of awards and stuff. That's mostly local kind of folks who've known
Mhm.
us and seen us, but we do get into that type of thing. Another interesting aspect is with our technology, because we're not getting hot, at any point we can stop and drop in an electronics package, a sensor, a device. And what we've done for a lot of customers, as well as some of our own internal folks, is we've made little coffee mug heaters, so we can embed a heater into the base of a metal part, as well as a thermocouple, so that we
Mm.
can turn that on and off with temperature. And it's all buried inside of this little plate that you sit on your desk. So there's lots of kind of interesting applications with embedding things to get functionality out of hardware that you just couldn't get with traditional types of manufacturing.
What about non-ferrous or non-metal layering?
Mhm.
Could you do a plastic and then copper, pathways through that with another plastic on top and create basically integrated circuits? Like, is that a thing?
So that's a fantastic question. So our welders are set up for welding metal. So ultrasonic metal welding likes scrubbing. Ultrasonic
Mhm.
polymer welding likes knocking into each other, kind of
Okay.
this kind of motion.
Yeah.
So we haven't done a lot of polymer work. So I don't think we have a good chance of mixing polymers and metals. Where we do play sometimes is mixing ceramics with metals.
Right. Because they're
And
crystals still. Yeah.
again, we can't directly weld with our process to a ceramic. Typically, what we do is we use another process, like a vapor deposition, to lay a thin layer of metal on the ceramic, and then we can print on top of that.
Right.
Um, so yeah, the polymers aren't. We just haven't got a good solution for jumping polymer to metal, at least with our technique.
Gotta start mixing those polymers with like graphites and stuff to kind of create like a
Yeah,
semi-metallic state or something.
exactly. Something that we can get a little bit of metal to metal contact.
Write that down. That might be your trick there.
Yeah,
No.
yeah, yeah. I'll put you on the patent.
So, what when I think about this process, it's all like it makes perfect sense. I love it. What about waste?
Yeah.
One of the things that comes up with any type of additive manufacturing now, there's been a lot of investment into additive manufacturing, but at the end of the day, the additive, the AM created part is generally not a finished to size part. There's always like some machining or refinishing that needs to happen around it. Um, is there a lot of waste in this? Like you talked about pre-stamping or just creating where you need to and milling as you go. Compared to other processes, is there a high level of waste or low? How does that stack up?
So we would say that it's a much lower amount of waste because we're just printing near net shape. So we may print, 2-3 millimeters wider than we need to, just so we have a nice face to mill. But
Mhm.
other than that, we're just printing the material where we need it to be. So, if we're milling a millimeter off of everything to clean it up, there's not a ton of waste to be had. Since all of our processing is happening in one machine at one time, at one go, there really isn't much post processing. The only thing that we may do is, if somebody wants a helicoil or something like that, that's going to be hand inserted afterward. But the hole is going to be drilled, tapped, in place as we're building. So there's not a lot of finishing to be done, once they come out of the machine. From a overall ecological standpoint, things like powders for some additive processes. Making powders is a very, very energy intensive
It is,
process.
yeah.
For us, we are taking metal foil. So at some point it was melted and put into a sheet, but that's being done at a very large scale as efficiently as possible. When we bring that in, we don't melt it. So we're not putting that much energy in the grand scheme of things, because everything stays at solid state, nothing really melts. The amount of energy we put in for unit volume is almost a tenth of what you would do with a fusion-based process. So we feel we're fairly, ecologically sound, trying to use the minimum amount of energy in order to get the bond that we need. And again, the feedstocks tend to be a little more, a little less energy intensive, although they are metal products.
Well, at the end of the day, metal's metal. There's a process there, and I find it interesting in the world. I'm getting old now. I'm coming up on 50, and I look at the waves of highs and lows of materials throughout my life. Even when it was like steel and glass are bad, stainless is important, and now stainless is too expensive and glass and metals are good again. Wood is bad, now wood is good, like that. And that's all based on technology. A lot of people don't understand. That's like, well, paper bags used to be the death of everything and now they're back. It's like, well, the technology in forestry has also changed. We produce paper way differently than we did 50 years ago. So there's things like that. But with this process, you still haven't gotten into, or maybe you haven't quite got to the level where, can someone come in and say, I'm a business owner, I want to buy one of your machines to set up, and I can rifle these off in my own shop? Are you at that point?
Yeah, we are. So we have what we call catalog machines, kind of a small, medium, and large, that anyone can come in and buy. And we do have those out, in shops around the world. In fact, we have one in Europe, one in Australia. The kind of the key piece of knowledge you need is if you know CNC milling pretty well, you're off to a really good start. You have to understand how a CNC runs. That's where most of it is. On top of that, you have to know a little bit about solid state welding, which with all machines, we pretty much, put in training, and we'll come out and train you on all the basics. And then, with our customers, typically, we're fairly tight in that they will contact, hey, we're going to weld, Inconel to steel today. You have any advice? And, we'll feed back to them, hey, these are our notes on kind of feeds and speeds. So just like you have a machinist handbook for milling, we have a handbook for welding. If you want to put Inconel onto steel, you use feeds and speeds A. If you want to put steel onto Inconel, it's a different feeds and speeds. But we share those with our customers if we have them. So that, kind of try and make it as easy as possible for them to go out and make some money with them.
One of the other questions I had was, after you're done building a part, it's machined and ready to go, it looks pretty, is there any annealing or stress relieving or anything like that has to happen to the finished product before it goes out the door, or is it ready for service at that point?
So it's a little bit dependent on the customer, and I'll kind of explain why that is. So earlier on, we talked about oxides, getting oxides included, and we do take a debit in the Z direction. So for many, I'd say most customer, that's fine. So a vast majority of the parts that we make, they are put into use directly off the machine. Now, when you get into some high consequence industries like nuclear, satellites, aerospace, anything 3D printed has to go through a specialized heat treatment called hipping. That's kind of derived from some of these powder-based processes, but a lot of the large OEMs just have a flat out, if it was made with additive manufacturing, it has to be hipped. So in those cases, some of those parts are being hipped. From my perspective as a metallurgist, it's a waste of time, but there's some thou shalts out there, and so we check the box when we have to.
Well, there's some industry standards that I'm sure get made to the lowest common denominator, which
exactly
you're not in that denominator, but still it's out there, right?
So, yeah, we're underneath that umbrella. So
now, and you have an interesting point of view. You came up in industry, you worked, you kind of did the hands on the tools type of job, which I love when engineers do that. I find that that's very useful in an engineer's career. Then you kind of went into like the think tank, you got thrown into the think tank, and you came out the other end kind of an entrepreneur, which is, a very interesting pathway. Now, for yourself, looking at the industry as a whole, How do you feel about, some of the issues that we're seeing in the industry with, the lack of tradespeople, or some of the skills gaps that are being happening across, our countries, Canada and the US? How do you see that?
Yeah, I see it as a travesty. I mean, we at Fabrosonic, we are working with our local area career center, trying to bring kids in and show them, hey, welding can be cool. Welding has high technology. Welding takes a lot of science. Trying to, pull people in and show them, how rewarding and how much fun some of these, very hands-on careers can be. But yeah, it's I think mostly driven by a lot of parents who still see our industry as, a lot of smoke and dirt, and they just haven't been in a high-tech manufacturing shop where, we're controlling the environment. We want to have, a controlled environment for our process and for our people. Yeah, it's something that we definitely battle. And every time we can, we're bringing students in. Like I say, from career centers, we've had high school interns where we brought them in, trying to get people excited about, hands-on work, running machines. We've had high schoolers run, printing parts for us. We have, yeah, it's a continual battle, and we're trying to do what we can.
Now, do you see the future of Fabrosonic in the development arena for putting materials together and creating the next technologies, or is it going to become kind of like a Miller Welding or a Lincoln, where you're kind of pushing machines out for productivity and for manufacturing?
So the technology is really new, right? I mean, we've been around 10 years, but it's still really new. There's not a lot of people that even have heard of us, much less experts on the subject. So I think for the next 10 years, at least, we're always going to have some component inside of process development where, somebody brings in, hey, I want to put A to B to C, and we help them with that process development. So I don't think we're ever going to lose that core development piece. Now, that being said, getting machines out there is certainly financially a great thing. And we also do production in-house. Last year, we made about 30,000 parts in-house using our own equipment. And I like that mix of, selling customers end product is great. It makes good money. Doing production in-house allows you to learn what are all the things that are keeping your customers from having success. So you run into the problems, you run into the
bottlenecks,
the little gotcha that you don't know about, and are able to continually improve the machines based on that. And then the research component, helps keep everyone excited, keeps everyone on the shop floor, interested in this new thing that we've never done before that, is going to help us in the long run. So I like that mix of having research all the time, having production all the time, and then, selling product out the back end. Now, we move up and down that spectrum a little bit. We do every year, but I think we always have to have those three key pieces inside our own walls.
And with the attachment of EWI, are they still feeding work to you as opposed to you having to go out and look for work?
No, we have our own sales staff.
Okay,
We're pretty much, we've been autonomous in kind of the sales aspect, most of our existence. Certainly, we do rely on or use EWI for services like materials testing. We always go to them for metallurgical mounts, SEM work. We always go back to home base. But other than that, we're pretty autonomous.
And then what about with the CWB? Now with this affiliation with the CWB, and I've talked to many people within EWI and around EWI. Some know so much about the CWB, some it was never even on the radar, right?
Sure.
It's like, what is that?
Yeah.
So do you see a connection with Fabrosonic and the CWB group and Canada, maybe just as a place of business?
Yeah, I think one of the huge benefits of the kind of the coming together of EWI and CWB is that they're both kind of targeted at a little bit different audience, and getting that cross ability to access those other audiences, I think, is great for not only the companies but also the end consumers, and that they get access to a lot of things that just really weren't on their radar before. From a Fabrosonic standpoint, it's the same thing. Working with you to get out to a broader audience, working with other CWB engineers to hey, if you have this problem, here's another solution that you may not have been aware of before. Anytime you get into, these spaces of highly technical, highly engineered components, there's never, one technology that solves everything, right?
Yeah.
You got to get every tool in your toolbox, and being aware of what tools are out there really allows, people to serve their customers better, because they have access to, things that, maybe they weren't aware of in the past.
Mm-hmm. Well, and that's awesome. And, with Fabrosonic's success, do you see much expansion in the future too? Is this like, multiple shops around the world type of thing? What are Mark's world domination plans?
Yeah, so we recently moved into a larger building for us. We have about 35,000 square feet, which is maybe a little bigger than we need right now, but we wanted room to expand both the manufacturing of products, making parts on a production standpoint, but as well as building machines. So we have enough space for maybe the next 5 to 6 years. Hopefully after that, things will continue to grow, and we'll move into another part of the existing building we're in right now, where there's room to expand sideways. I don't think there's ever going to be a need for multiple sites. We ship machines all over the world right now. The thing that we need to expand is maybe our network of support people. But again, the machines are based off of CNC mills, so partnering with organizations that already do maintenance and repair of CNC mills, they'll understand our equipment very, very quickly. It's not like we need to develop a new skill set. We just need to find folks who have that skill set.
Right. Awesome, buddy. Well, this has been a lot of great information, and I learned lots today. And I as with most of these interviews, I wish I had one of your toys to play with in my garage, but I don't know if it'll run off 240, so probably not.
No, now, it's been a lot of fun talking with you. I appreciate the time.
You bet. So what's on the game plan for Mark now? Where do you want to be in 10 years, or when you grow up? Do you see yourself just riding this? Is there going to be a baby Fabrosonic offshoot that takes your interests? What do you see for yourself?
Wow, that's a great question. Kind of how I mentioned, I've kind of fallen into everything I've done. I've kind of been at the right place at the right time. Fabrosonic, I started on this technology in 2007. So I'm going on, 16 years now with this technology. It's kind of my baby. If someone says, ultrasonic additive is no good, that really gets under my skin. So I'm probably going to end up here for a while longer. I've been working with this technique for a long time, and I really want to see it grow and explode. So
that's awesome. Well, to close it out, how do people find out more about your company? How do people know where you are? Let everybody know, the pathways to get to you.
Yeah, the easiest way is to go to the web, fabrosonic.com. If you want to see kind of videos of the technology in action, on YouTube, if you put in Fabrosonic, we have a bunch of videos of different parts, different machines running, just kind of show how it works. But go to the website. You can also email us at info@fabrosonic.com. We're fairly easy to get a hold of.
Awesome. And if someone's interested out there and they reach out to you, I'm sure that they're going to have a really good time trying to figure it out. Because I would love to see someone just be like, oh my God, I could do this to that. Maybe they can help us, right? That would be really cool.
Now there's a lot of good problems out there. Like I say, knowing what tools are in the toolbox, see if you have an option.
And what's what was I going to say? Or what were some of the last things you'd like to get out there? Anybody you want to say thank you to? Anybody you want to say hi to? Any shout outs? Yeah,
let's see. Our biggest customer who's doing automotive, I can't say your name, but Mark and Joe, love to see you guys out there. And to all of our friends at EWI, as I mentioned, I came out of EWI. I have a lot of great friends there, so always like to give them a shout out.
Well, I'm going to be down visiting EWI in Buffalo though in December. So I
Yeah.
don't know if you know many of the people in the Buffalo, but
Oh, for sure.
facility, but
Yeah.
I'm excited to go there. I missed the first round of tours because I was sick, but this I'm going down there to do some visits, and I can't wait to get down to Columbus to see that shop. But I'm waiting to see when the Browns are playing nearby, so maybe I can
Perfect.
time that really well.
Yeah. If you're ever in Columbus, let us know. Like I say, we're only 15, 20 minutes away, so we'd love to
Yeah,
have
I would
you
love
out.
to see the shop. I would love to get a tour.
Yeah.
Awesome. Well, thanks, Mark. It's been super wonderful. Like you said, check them out on Fabrosonic.com. They're online. Lots of really cool stuff. If you're interested in the technology, check out the videos on YouTube. And of course, with the release of our podcast, we're going to put all the links up and share them out there for all our memberships and all the people that follow along. So thanks again, Mark, for taking time to be on the show.
Thanks, Max.
All right, everyone, keep downloading and sharing, and we'll catch you at the next show. Take care of yourself.
We hope you enjoyed the show.